This is the solution to example 5 from notes 3.4. In this problem, we're given a polynomial function of fifth degree, and we would like to find all the zeros. But as we saw in example 4, testing for the zeros using synthetic division can get tedious, and if we don't guess well, or if we have a lot of factors of the constant term and the leading coefficient, there could be a lot of zeros to test. So in this problem, what we're going to do is we're going to use our graphing calculator just to find the rational zeros, and then we're going to use synthetic division to verify the zeros and then to completely factor the polynomial. So the first question is, letter A says, how many zeros does f of x have? Because it's a fifth degree, that means this polynomial will have 5 zeros, right? The number of zeros is equal to the degree. Okay, so letter B says, find all zeros including their multiplicities of f of x, and then write f of x as a product of linear factors and quadratic factors that cannot be factored over the rational numbers. So this is the typical way we factor quadratics. Okay, so we're going to use our graphing calculator. So I would recommend that you pause the video and go ahead and graph this function, and once you do, come back. I'm just going to sketch the function myself because I don't want to integrate the graphing calculator into this video. So go ahead, graph the function yourself, and then come back. So I've sketched the function on the page here. So we can see from the graph that we have 2 zeros. These are apparent zeros. We don't know for sure. So we have a 0 at -1 and at 2. And the multiplicities, the multiplicity of the 0 at -1 is odd because the graph crosses the x-axis when x is -1, and the multiplicity of the 0 at x equals 2 is even because the graph bounces off the x-axis there. So we have even multiplicity when x is 2. So we're going to use this information rather than the rational zeros test in order to start factoring this polynomial. So we're going to start using synthetic division. I'm going to put the coefficients of f of x in the first row. You'll notice there are no missing terms, so we don't need any placeholders. So I'm going to put 1, -5, 9, -5, -8, and 12 across the first row. And now I can choose the zeros in either order. So I'm going to start with the 0 at x equals 2. So this is one of our zeros. And we should confirm, this should confirm that x equals 2 is a 0 if we get a remainder of 0. So bring down the 1. 2 times 1 is 2. -5 plus 2 is -3. 2 times -3 is -6. 9 plus -6 is 3. 3 times 2 is 6. -5 plus 6 is 1. 2 times 1 is 2. -8 plus 2 is -6. And then 2 times -6 is -12. So we did get a remainder of 0. So we've confirmed that 2 is a 0 and x minus 2 is a factor. And now we've reduced our fifth degree polynomial and to a fourth degree quotient. We've reduced the degree by 1, and we're going to do synthetic division again. So since the 0 at x equals 2 has even multiplicity, that means that we can do synthetic division again with x equals 2, because the lowest multiplicity that this could be would be 2. That's the smallest even number. So let's do synthetic division again with the 0 at 2, and we're going to do synthetic division in succession so we can continue to reduce the degree of this polynomial function, our quotient, and continue to factor it. So bring down the 1. 1 times 2 is 2. -3 plus 2 is -1. 2 times -1 is -2. 3 plus -2 is 1. 2 times 1 is 2. Nope, I wrote that the wrong place. 2. 1 plus 2 is 3. 2 times 3 is +6. -6 plus 6 is 0. Yay. So now we can say that 2 is a 0 again, and x minus 2 is a factor again, which is what we expected based on the graph. Okay, so now we've gone from a fifth degree to a fourth degree to a third degree. So we have one more 0 from the graph that we can verify. and that's going to be the 0 when x is -1 from this x-intercept. So we're going to go ahead and put -1 outside the L, and then we'll bring down to 1. 1 times -1 is -1. -1 plus -1 is -2. -2 times -1 is +2. 1 plus 2 is 3. 3 times -1 is -3. And we have confirmed that -1 is a 0 and x plus 1 is a factor. And now our remaining quotient, which we're going to find from these coefficients, has been reduced to a second degree polynomial, or second degree factor. So let's go ahead and write f of x using the factors we know so far. So we know that f of x is equal to x minus 2 squared, because we had that 0 twice, times x plus 1, times the quadratic factor here will be x squared minus 2x plus 3. So I'll add that in. So x squared minus 2x plus 3. And this is what we were asked for. In the problem description, we were asked to write f of x is the product of linear factors, so that's like the x minus 2 squared and the x plus 1, and quadratic factors that cannot be factored over the rational number. So we can't factor x squared minus 2x plus 3 further. So we're going to leave that as a quadratic factor. Okay, now we need to continue on to find all the zeros. So for that, we can find the zeros of the quadratic factor. Okay, so I will complete the square here. The last example, I think I used quadratic formula. So I'm going to complete the square to find the zeros of x squared minus 2x plus 3. So we have x squared minus 2x plus 3 equals 0. I will subtract 3 from both sides of the equation. And now we need to add the number, which will make x squared minus 2x a perfect square trinomial. And that number is b over 2 squared. So b in this case is -2. So -2 over 2 squared is -1 squared, which is 1. So we'll add 1 to both sides of the equation. The reason we did that is now we can rewrite x squared minus 2x plus 1 as a binomial squared. So this will be x minus 1 squared is equal to -3 plus 1 is -2. I'll take the square root of both sides. So x minus 1 equals plus or minus the square root of -2. So x minus 1 is equal to plus or minus I rad 2. And then I will add 1 to both sides of the equation. So we get x is equal to 1 plus or minus I rad 2. So we have two imaginary zeros. Notice that we have a number and its complex conjugate. So finally, we will list the zeros. So we have 2 that has a multiplicity of 2, -1, which has a multiplicity of 1, and then 1 plus or minus I rad 2. Each of these has a multiplicity of 1.